Acid comes from the Latin word acidus for sour, like lemons, and alkali comes from the Arabic word for calcinated plant ash, which is mostly composed of potassium carbonate, that's basic. Many common acids can be found in food and drinks, like orange juice and soda. Common acids for us are acetic acid and vinegar, hydrochloric, and sulfuric. Common bases include soaps and detergents, and baking soda, which is sodium bicarbonate. For the properties of acids and bases, acids turn litmus paper red and bases turn litmus paper blue. Acids typically taste sour like lemon or vinegar, don't actually taste bases, but they taste bitter in comparison. Acids are considered corrosive, whereas bases are caustic. And on the bottom, we have a couple different definitions for acids and bases. Acids increase the concentration of hydrogen ions in water, and that's because they donate hydrogen ions. Bases increase the concentration of hydroxide ions in water, and that's because they accept hydrogen ions. So hydrogen ions are transferred from the acid to the base, and we'll go over more about that when we talk about Arrhenius and Bronsted-Lowry theories of acids and bases. First, a quick explanation for some terms. Hydrogen, or neutral hydrogen, is one proton and one electron. Hydrogen with a +1 charge is missing that electron, so it's just one proton. So we often refer to hydrogen ions as just protons. When hydrogen ions are in aqueous solution, they combine with water to form hydronium ions, or H3O+. So these three terms are used interchangeably. We can say protons, or hydrogen ions, or hydronium ions, and we can write H+ or H3O+, and it all means the same thing. The Arrhenius definition of an acid is that it forms hydronium ions in water, and a base forms hydroxide ions in water. So if we see that HCl with water forms H3O+, that means HCl is an acid. And since we see that NH3 with water forms OH-, that means that NH3 is a base. But this definition only works in aqueous solutions that contain water. Since not all solutions contain water, we're going to focus on the Bronsted-Lowry definition of an acid and a base. According to the Bronsted-Lowry definitions, an acid donates a proton and a base accepts it, so H+ is transferred from the acid to the base. On the left, we can see that HCl donates H+ to water to form H3O+. That makes HCl the acid because it's donating the proton, and it means that water is the base because it's accepting it. On the right, water is donating H+ to NH3 to form OH-. That makes water the acid because it's donating a proton, and it makes NH3 the base because it's accepting it. Notice that in these two examples, we can see that water can act as an acid or a base because it can donate a proton or accept it, depending on what it's with. That's called amphiprotic. So here are some common ways to identify acids and bases. Acids can include common anions with an H+ because they have a proton that can be donated. And bases can include common anions without an H+ because they're able to accept a proton. Acids are also anything with a carboxyl group, which is COOH. For example, I drew acetic acid, which has a CO double bond on top and an OH at the end, and this H+ at the end is the one that comes off and can be donated. The other hydrogens on the left are stuck in place. And that forms acetate, which is a common base, or really anything with COO- because it's able to accept a proton. Ammonium, or anything with 4 things around nitrogen, is another common acid because it can donate a proton. And ammonia, or anything with 3 things around nitrogen, is a common base because it has room to accept a proton. One important thing to note is that acids donate protons one at a time. If they're monoprotic, that means they only have 1 proton to donate. Diprotic acids can donate 2 protons, like H2SO4. Triprotic acids have 3 protons to donate, like H3PO4. And polyprotic means it can donate more than 1 proton, so that includes diprotic and triprotic acids. Amphiprotic are substances that can act as an acid or a base, like we saw earlier with water. Conjugate pairs are acid-base pairs that differ by 1 proton. So the acid has 1 more proton than the base. Acids donate H+, so its conjugate base is whatever's left after the proton is donated. When HCl donates H+, we're left with Cl-, and when acetate donates H+, we're left with CH3COO-. Remember that the H plus at the end of the COOH carboxyl group is the one that's donated. And don't forget to pay attention to the charges. Losing a positive ion should leave a neutral acid with a negative conjugate base. Bases accept H plus, so its conjugate acid is what's formed after the base accepts a proton. NH3 with a proton will form NH4 plus, and NO3 minus with a proton will form HNO3. Again, pay attention to the charges. Don't forget to add +1 to the overall charge since the proton is positive. The example on the bottom says to identify the conjugate pairs in the equations and label them. These are the same equations we used earlier. On the left, HCl donates a proton to H2O, so the HCl is the acid and H2O is the base. The conjugate base is what's left after the acid donates a proton. So when HCl donates H+, we're left with Cl-. And the conjugate acid is what's formed when the base accepts a proton. So when H2O accepts H+, it forms H3O+. On the right, H2O donates a proton to NH3, so H2O is the acid and NH3 is the base. The conjugate base is what's left after the acid donates a proton, so when H2O donates H+, we're left with OH-. And the conjugate acid is what's formed when the base accepts a proton, so when NH3 accepts H+, it forms NH4+.